Hello everyone, my name is Qin Hao. I'm a PhD student from Technological University. I will be presenting our characterization and prediction of deep learning workloads in large-scale GPU data centers. This is a joint work with Peng Shenggen from SenseTime and my supervisor Tenwei Yonggang from Nanyang Technological University. Firstly, I will introduce the background and explain why GPU data center is needed. Nowadays, deep learning application become ubiquitous. SenseTime is one of the largest AI firms in China, and that we have empowered AI technology into over 10 fields, including computer vision, speech recognition, recommendation, and some emerging fields, such as city management, autopilot, and healthcare. To facilitate this application, SenseTime built several GPU data centers, and Helios is one of the data centers in SenseTime, contains over 10,000 GPUs. Helios supports all the workloads for deep learning development pipeline, such as data preprocessing, code debugging and testing, hyperparameter and model architecture searching, as well as distributed training. Users submit their job to compute node in Helios through Slurm scheduler, and this GPU training job typically based on mainstream framework like TensorFlow and PyTorch. In Helios, to accelerate the training process, each compute node equipped with 8 GPUs and interconnected with the InfiniBand. Comparing with conventional HPC workloads, deep learning training jobs have several unique features. First is the iterative process. The target model is obtained through the gradient descent update iteratively, and the long-term training process can be suspended and resumed through checkpoints. Second is the feedback-driven exploration. User can inspect job training state and use early feedback to decide whether to kill the job. Further, deep learning training jobs typically utilize GPU to speed up the matrix computation. They require a number of GPUs as dominant resources, as well as other associated resources such as CPUs and memories. And multi-GPU jobs usually perform gradient synchronization to update model parameter at the end of each iteration. Better locality and interconnect topology can achieve lower communication overhead and faster training speed. The gun scheduling and the exclusive allocation features are similar with HPC work jobs. Because of these features, existing HPC scheduler cannot fully utilize the cluster resources. The characterization study of deep learning workloads is needed for future research. To this end, we collect job metadata from Slurm job logs and form Helios trace. It contains rich information such as job GPU number, job name, final status, submit time. In this work, we select 4 representative clusters from Helios. They are Venus, Earth, Saturn, and Uranus. Each cluster contains more than 1,000 GPUs, and there are over 6,000 GPUs in total. We collect trace from April to September in last year. It spans 6 months, and there are over 3 million jobs. Around a half are GPU jobs, and the others are CPU jobs. These GPU jobs request 3.7 GPUs and execute 1.8 hours on average. We also can find some jobs request over 2,000 GPUs and last more than 1 month from the trace. Our study contains 2 parts. In first part, we focus on the characterization of Helios. We will give comprehensive analysis from the perspective of clusters, workloads, and users. So, can we get some enlightenment from the characterization studies? We first analyze cluster usage trends. This figure shows the average cluster utilization for each hour in one day. Overall, the utilization of all the clusters ranges from 65% to 90%. This cluster have similar diurnal patterns for the daily cluster usage. So what does this mean for future research? This implies there exists opportunity to predict cluster resources usage in advance. We propose CES service based on this observation, and we will present in the next part. It's designed for energy conservation, uses GBDT model prediction. Besides cluster utilization, job throughput is another important attribute. This figure shows the average GPU job submission rate for each hour during one day. GPU job submission frequency in each cluster ranges from 50 to 200 jobs per hour. This is typically lower than big data cluster and do not have such a strict scheduling latency requirements. This inspires us that applying time-consuming scheduling algorithms to GPU data center is possible. Our group proposed a novel scheduling system called Corners. It's designed for deadline-aware scheduling using a MILP server. It has published in SOCC 21. In addition, we perform comprehensive analysis of workloads. The left finger shows the CDFs of the requested GPU demands with number of jobs. We observe that there are over 50% single GPU jobs in each cluster, and the largest ratio is 90% in Earth. However, they only occupied less than 10% of the total GPU time in each cluster, as shown in the right finger. To confirm our observation, we further analyzed monthly trend of GPU resources and job behaviors. In the top finger, the hatched bar represents monthly multi-GPU job submission number. We can find it exhibits much more stable monthly pattern comparing with single GPU jobs. The bottom finger presents the cluster utilization contributed by single GPU and multi-GPU jobs. It is evident that single GPU jobs have little influence on the overall cluster utilization. Therefore, in future research, we should focus on the optimization of multi-GPU jobs, even though there are a large fraction of single GPU jobs. This is critical for improving cluster efficiency. And the job GPU number should be considered in the scheduling algorithm. This will be reflected in our QSSF service. We will introduce it in the next part. We also find some interesting observation with regard to job final status. The left finger summarizes the distribution of final status for CPUs and GPU jobs of these four clusters. We can see unsuccessful GPU jobs takes around 40%. In the contrast, over 90% of CPU jobs completed. In the right finger, we quantify the ratio of different job final status in terms of GPU demands. It is obvious that the more GPU numbers, the less completion ratio. One reasonable explanation is the feedback-driven exploration, which is one of the deep training important features. To train a job, users typically try several configurations and use early feedback from these jobs to decide which one should be kept or killed. This gives higher consideration ratio in GPU clusters. Some users prefer to terminate their training jobs in advance, as the model accuracy already converges to the satisfactory value. This cancelled job can actually be regarded to successful. Another reason is that users can inspect the training state and kill the poor-performing jobs earlier. This feature can be leveraged by GPU data center scheduler to early stop training jobs. This can significantly improve data center efficiency. We also analyze the job final status of Microsoft Philly workloads. As shown in this finger, we can see the percentage of GPU time occupied by jobs with different status in both Helios and Philly. There is a significant fraction of GPU time contributed to the job which are finally end up with the failure on the cancelled status, which imply large amount resources are wasted. It is common in SenseTime and Microsoft. For future research, it implies early error detection and eviction is an important direction for data center efficiency optimization. So far, we have discussed cluster and workloads characteristics to discover approaches for user experience enhancement. We perform trace analysis from the user perspective. Similar with traditional HPCs, most resources are used by a few users. As shown in the figure, we find the trends are similar across all the clusters. Compared with the GPU times, the CDF curves of CPU times are more steeper. The top 5 users consume around 50% GPU resources in each cluster, and the top 5 users occupy over 90% CPU resources in each cluster. Next, we studied the distributions of GPU job queuing delay among users. We observed that most users do not suffer from severe job queuing, whereas a few users have job blocked for a long time. In neurons, the top 1 users bear over 70% queuing time, even they are not the top resource-consuming users. They suffer severe queuing because their job preference. Large-scale jobs typically require much longer queuing time. From this observation, we find scheduler can perform user-level optimization to alleviate failed cluster queuing. For instance, the scheduler can dynamically adjust temporal priority to users, especially to the long-blocking users. In the second part, we will introduce a prediction-based framework and we will design two surveys, QSSF for job scheduling and CES for power conservation as case studies. So we will present how to leverage the trace data to optimize GPU data centers in this part. Based on previous characterization work, we find historical data to be used to improve cluster efficiency. Here is our prediction-based framework overview. It adopts a plug-and-play fashion, where different resource management services can be integrated into this framework. It contains two main components. Resource orchestrator, shown in blue block, determines operation according to machine learning model inference. And the model update engine, shown in green block, fetch the runtime data from physical cluster and fine-tune the model periodically to adapt to the changes in the cluster. As case studies, we designed two novel services. Quasi shortest service first scheduling QSSF to minimize the cluster-wide average density, and the cluster energy saving CES to improve cluster energy efficiency. I will introduce them separately. The largest challenge for minimizing density is the unknown execution time of deep learning training jobs. If we have the duration of each job, we can apply existing optimal scheduling algorithm. Shortest job first, SJF, and shortest remaining time first, SRTF. These two algorithms can efficiently reduce density with or without preemption, but they require perfect duration information. This is impractical. So our objective is to minimize density with partial job information. We find some important observations can help us achieve better prediction performance. Firstly, users have individual job preference and duration patterns. Some users only submit one GPU short-term jobs, while distributed training jobs are necessary to other partial users. Secondly, there exists a strong correlation between the job duration and some attributes such as job name, user, and the GPU number. Further, for the same user, the same or similar job name often indicates close job duration. For instance, in our case, users submit 265 GPU jobs to Saturn in September. 181 of them were named as Python, with approximate 3 minutes of duration, while around 70 jobs have the name format of extract something, run for roughly 5,000 seconds, and 8 jobs named as list something stage last around 100,000 seconds. The job name is noteworthy attribute to estimate duration, because lots of users need to perform hyperparameter search. This will bring a lot of similar jobs. We choose to use GBDT model to capture the overall trends of the jobs. For the job name features, because it is extremely sparse and high-dimensional feature, we utilize the Lagrangian distance to cluster the names and buncsize similar ones. This greatly improves prediction accuracy. And for the time-related features, such as job submission time, we parse them into several discrete attributes. The QSSF scheduling algorithm schedules the job according to the priority value P. Here, P sub M represents the GBDT model estimation, and P sub R represents the estimation simply rolling from user slot. We combine these two values together and times job's GPU time and obtain job priority P. Although it cannot guarantee high predict accuracy, this heuristic finding performs well in our evaluation. We perform evaluation based on September job trace across 4 clusters in tiers. This figure shows CDF curve of JCT in each cluster with different scheduling algorithms. We observe that our QSSF algorithm can significantly outperform the FIFO policy. It is what we are using in SenseTime and perform comparably with the SJF. We further evaluated QSSF on smaller clusters to examine its sensitivity. We select the top 10 virtual clusters called VCs with the highest average queuing time. From the last column, we find average queuing time of QSSF is almost identical to SJF. For other columns, we can see QSSF remains stable performance in each VC. We designed another service called Cluster Energy Saving. We find tremendous energy wasted on idle computing nodes. And our objective is to reduce energy consumption from those idle nodes while satisfying users' demands. In this service, we still choose GBDT model to perform time series forecast because it outperforms other models such as ARIMA, Prophet, and LSTM. We encode the repetitive patterns of running nodes to explore the periodical variance and extract trend and seasonality on the different rolling window size. After training the model, we obtain future node trend estimation. To make the cluster more stable, we consider recent node trends in addition to determine the final operation. We present evaluation based on 3 weeks trace on September in Earth. As shown in this figure, the gap between the red and the green line represents the nodes to be optimized by our CES service. On average, CES set 20.5 nodes as sleep state, and only trigger nodes wake up around 1.3 times per day. According to our estimation, CES only can save over 1.6 billion kilowatt-hours of electricity annually across 4 clusters. In summary, our work performed a detailed characterization study of a large-scale GPU data center Helios at time. Based on this observation, we uncover several implications for future system design. Further, we introduce a general-purpose framework to optimizing data center based on traces and make 2 comprehensive case studies. More analysis and evaluation can be found in our paper. The Helios trace and the scripts are available at this website. That's all. Thanks for your listening.